All right, so this is going to be the last portion of Physics 1C for today. And what we have is a sphere inside a spherical shell. So we have a solid insulating sphere of radius A. That's this one here. Carries a net positive charge, big Q, uniformly distributed throughout its volume. So this is the insulator, the red one. And the charge on that one is distributed uniformly throughout. Okay, not on the surface now, because it's an insulator. If it was a conductor, that wouldn't be possible. But because it's an insulator, it is possible to have the charges just smeared throughout the entire thing. Okay, it has a net positive charge Q, a conducting spherical shell of inner radius B, so that's going to be this blue shell here, and outer radius C, is concentric with the solid sphere and carries a net charge negative 2Q. So this one here is negative 2Q. This one's Q. Using Gauss's law, find the electric field in the regions labeled 1, 2, 3, and 4, and the charge distribution on the shell when the entire system is in electrostatic equilibrium. That phrase that we just talked about. All right, let's put this up here and go down just a little bit. So that's our system, and we basically just want to find the electric fields everywhere for R less than A, R between A and B, R between B and C, and then R greater than C. Okay. All right. So this is a bunch of Gauss's law things we're going to be doing here, and I guess what we should do is we should get our own thing to draw on here. So we'll start off with our inner circle, which is red. Can I fill it in? It doesn't matter. I'll just fill it in with charges. So there's our inner circle, and then we're going to have our outer circle out here. Do my best to square it up. We'll make it blue, and that one has two sizes to it. There's going to be another one right around it. We're going to end up drawing a lot of circles in this problem, so... And let's see. So let's just indicate that these are positive and negative by saying this one's the positive one. I'm going to have to draw a bunch of charges. These ones are smeared all throughout it, right? Now the other one, I'm just going to say that it carries charge negative 2Q, because I don't really know how we should draw these charges. What I mean by that is I don't know if I should put, and this one's big Q, right? I don't know if I should put a bunch of negative charges on this inner surface here, or if I should put them on this outer surface here. And what we're going to find out is that we really have to kind of solve the problem before we know where they're going to be, okay? So we'll just say that this is negative 2Q. We don't really know how those charges are distributed. They're in here somewhere, and later on we will fix the arrangement. Like we'll put them on the outside if they're on the outside. But that is one of the things we want to figure out, right? It says, using Gauss's law, find the electric field in all the regions and the charge distribution on the shell. Out here, basically, right? Now, in the gap between the two of them, there are no charges, okay? So we got radius A for this one, and then we've got radius B goes out to here, so that's B, and leaves one other color, I guess, for C, which goes all the way to the edge, right? So then there's C. There. Okay. So first thing to do is to find the electric field in the region that is R less than A. Now, in order to do this, we're going to use Gauss's law. So we're going to say the surface integral of E dot dA is equal to the charge enclosed divided by epsilon naught. We've actually already done this, but I'm going to go through the derivation again. So to do this, we of course have to draw a Gaussian surface. What our Gaussian surface is going to look like is going to be, a circle. I hate the way this thing works. Okay. We'll do that. We'll do that. Just make it smaller. So that's going to be my Gaussian surface. We'll draw it right here on the inside. And it's a circle. And what we'll be able to say is that the electric field in this region should be pointing kind of out this way. And the surface vector here is going to point in the same direction, so you're going to have a dA vector that's parallel to that. That allows us to say that E and dA are going to be, this whole integral is just going to turn into electric field times the area of the Gaussian. And the right-hand side, Q enclosed. Because the charges are uniformly distributed right here, I'm going to say that the amount of charge enclosed, in this case, should be equal to the charge density, which is Q, divided by the total volume, which is 4/3 times pi times a cubed, multiplied by the volume of the Gaussian, basically, which is basically 4/3, well, 4/2, 4/3 pi multiplied by the radius of the Gaussian. Let's define the radius of my Gaussian here to be r. So this is going to be times r cubed. And then all of this, of course, has to get divided by epsilon naught. Okay? If I take the ratio of the volume of the Gaussian divided by the total volume of that red sphere there, then I'll get the amount of charge that's actually enclosed within the region of the Gaussian. Right? That black little region right there. And we did this before, so.
Hey, Professor.
Yeah.
Real quick, why did you multiply for like the volume at the top of the fraction?
This is what we're doing.
Oh, okay.
Yep. All right, so the 4/3 cancels out. For the area of the Gaussian, what we want there is the surface area, which is the 4 pi r squared, the surface area of a sphere. We're left on the right-hand side with q r cubed divided by epsilon naught a cubed. And one of the r's cancels. All of these cancel. Only one of those cancels. And we end up getting E is equal to q divided by 4 pi epsilon naught a cubed multiplied by the distance r. So this is going to be the electric field in the region where r is less than a. And we did this yesterday, actually, or Tuesday when we last met. We solved this exact same thing. Okay, any questions? I'm going to get rid of the Gaussian now, because it's just going to look bad as we continue to do this. All right, the next region that we want to do is between B and C. So for this region, I'm just simply going to state that if you're in this region right here, that you're now outside of this spherical object, and what we found is that in that kind of a region, that the electric field just basically acts like a point charge. So the electric field of a point charge. So this is going to be for the region where A is less than R is less than B, right? Yeah. And you might ask, well, what about the shell on the outside? And the thing is, like, the shell on the outside doesn't matter, because if I were to draw a Gaussian surface in here, right, that Gaussian surface would only contain charges from that inner portion. So, all right, again, we actually did this, both of these yesterday, when we talked about the electric field of a solid insulating sphere that carries a positive charge Q uniformly distributed. Okay, so we've already kind of done those parts. It's the other part that's going to be new on this problem. Okay, so what happens when we get into the region right here? So when we get into the region where, what is that going to be? B less than R less than C? What's going to happen now? So this is where we have to go back here and look at the fact that this was a conducting spherical shell, right? This is a metal. Right here, this piece is a metal. Right? So can anyone tell me, what would the electric field in that region be?
It's got to be 0.
Yeah, it's 0, exactly. And that just goes back to number 1 right here. The electric field is 0 everywhere inside the conductor, whether the conductor is solid or hollow. And even though there's an external field in the region, it doesn't matter. It's a piece of metal. So that's it. Okay, so we've gotten all of our regions. We just have one more to go. We need the region that's called 4 up here. Okay, I could label these. This was region 1. This was region 2. This is region 3. And for region 4, we're now out here, right? This is for R greater than C. Now for this one, not a lot of room to use here. Can I move this whole thing down? Let's see. Okay, pulled some other stuff, but not a big deal. Fix that. So this goes back up here. All right. So now what we want to do is we want to get this outer region right here. So in order to do that, I need to draw a new Gaussian surface. This Gaussian surface needs to enclose everything. Like that right there. Seems fine. And again, we need to kind of draw some electric field lines and do all that stuff. So now, if you think about what's going on here, you have a negative 2q right here, and you have a positive q right here. So my guess would be that our electric field lines should point like this. You know? They should basically be pointing kind of towards that negatively charged system right there. And I say that because there's a total charge of negative q when you sum up this one and this one, right? So I think that's the direction of the electric field. And the direction of the surface that we've drawn, the Gaussian surface, again, this is our Gaussian. So the direction of the surface vector here is going to point this way. And yeah, that's the electric field on the other side. So now when we do our equation, we're going to say, okay, integral of E dot dA is going to be equal to charge enclosed divided by epsilon naught. So when we do the left-hand side here, oh, the chat's blocking. Okay, we'll go to the other side. Thank you. All right. Maybe it was better with the chat in the bottom right. I don't know. I moved it up there yesterday because there was some problem I was doing, but okay, there we go, like that. So how much charge is actually enclosed within our Gaussian here?
Negative q.
Yep. And the left-hand side of our equation here is basically just going to be, it's going to become negative EA, I guess, because there's going to be a 180 degree here. I don't know how important that negative sign is here, because ultimately, really all we're finding is just the size of the field, right? The surface area is going to be 4 pi r squared. And so now our electric field ends up being q over 4 pi epsilon naught r squared. But what I would say is that if we were to write this as a vector, the vector direction needs to point inwards. So it would be like this. And there we go. We still need to do the surface charges, but does anyone have any questions about that? I put the negative sign back in here because we know that it has to go inwards. All right, so the last piece of this was to figure out our surface charge distributions. So let's get rid of some of these lines that we don't really need anymore. And let's just figure out how these charges are actually distributed. Okay, we know in the blue region right here that the electric field was equal to 0, right? But we also know that this object carries a total charge that's called 2q, right? So if we imagine that we drew a Gaussian surface inside of that region, right here. then what we could say is within that region, we know that if we did Gauss's law, it says that integral E dot dA is equal to the charge enclosed divided by epsilon naught, right? But we know that this piece is 0 because E is 0. So that means that 0 has to be equal to the charge enclosed. Don't worry about the epsilon naught. We can just multiply it to the 0 side, right? So what that means is that 0 should be equal to the amount of charge that shows up on the inner surface right here. There's going to be some charge that goes to the inner surface right here. Okay? And I'm just going to go ahead and draw it because I know what it's going to be. I know it's all going to be negative. I'm just going to draw it on there and say that we call that the charge on the inner surface. Q inner. Plus the charge contained within this piece right here, which is big Q, right? Go through that one more time. We make a Gaussian surface. We put the Gaussian surface on the inside of the metal, on the inside of the shell. That Gaussian surface then encloses the charges that show up on the inner surface right here, and it also encloses the charges that are at the center with this insulating sphere. And that sum, because of Gauss's law, has to sum to 0, right? So what that means is that the amount of charge that shows up on the inner surface, what's it equal to?
Minus
Negative
the
Q.
big Q.
Yeah, negative Q. Okay, so now we know how much charge shows up on the inner surface. And I think the problem actually asked to find like the charge density or something like that. No, just charge distribution. Okay. We could find density. I think you all have a problem where it might ask you to find density. All we need to do is just divide that by the surface area of the inside here. Divide by 4 pi b squared. That would give us the charge density. But okay. So we now know that a bunch of negative charges show up on the inside there, and we know that because of Gauss's law, right? Okay. So how much charge has to show up? So now that we know on the inside here that this is negative Q, so we got negative Q right here, positive Q on the inside. How much charge has to show up on the outer surface now?
Negative.
Minus Q.
Another negative Q, right? That's because we now know that the total charge, this should have been negative 2Q, I apologize. The total charge on the shell was negative 2Q, and that should be equal to the charge on the inner portion plus the charge on the outer portion. And we know this is negative Q, so you add that to this side, and you get your answer for how much charge is on the outer surface, basically. Which is going to be, as you all said, just negative Q. So now we basically have our charge distributions. Negative all around here. Negative, negative, negative. And it's negative Q right here, and we can basically get rid of this piece now. So you get no charge inside on the shell, okay? So this region right here, no charges in here, but you do get charges on the inner surface and the outer surface, and those are their quantities. Those are their values right there. Does that all make sense?
Mm-hmm.
Now I'm going to change the numbers real quick here, because I think this problem is too simple. I mean, it's a good problem because it's a textbook problem, so it's like, you know, it's supposed to be simple, right? But what if we changed what if we changed a couple things here? Let's before we change something, I'll just stop for a second, because I went through that all really fast, I think. Does anyone have any questions? Okay. What if we do what if we do this? What if I make it so that this charge was positive 5Q, okay? And we make it so that the amount of charge contained on the outer shell, what if we change it to negative 3Q, okay? Can anyone tell me how much charge is going to show up on the inner surface then?
I would say negative 3Q.
No?
Or
Someone else want to try? So I make this one positive 5Q. I make this one negative 3Q. Okay, and now we don't know how much charge is on the inside, on the outside, right? We don't even know if they're positive and negative, so I gotta get rid of all those too. Think about it for a second. How much charge would then show up?
The inside wouldn't
Negative 5Q?
5Q.
Negative 5Q, yeah. And how did you all get that?
Well, we know that the electric field inside the shell has to be 0, and that...
Yeah. That's right, exactly. So that means that we could go through the same argument we did here. We would replace this with 5Q, and then that would mean that Q inner would have to be negative 5Q, right? Okay, so now we know we got negative 5Q on this side, right? Now how much shows up on the outside?
Must be
Positive 2.
positive 2.
Positive 2, yeah, right? Okay, so now what we know is we changed this because we know the total is negative 3Q. That's to be equal to this, but this has now become negative 5Q. So you add the 5 over here, and what is it? Negative 2 plus 5 is positive 3, right? Is that what you all said? Or did you say 2?
No, it has to be positive 2Q.
Oh, I'm stupid. This is still 3. Negative 3, negative 3. This becomes positive 2. Yeah. Okay. Positive 2Q right here. And negative 3Q is the total.
Okay. So that's what I was getting tripped up on. Like, you can have...
This would work out a lot better if I just did a whole new problem and just said, oh, what if we just check? But I'm just kind of trying to, But so it's kind of weird, right? Because now what happens is that you see that all of these charges basically, they suck all the way into the inside until they basically cancel out with what's inside, right? So you end up negative 5 and positive 5. But even though this object carries a total charge of negative 3Q, it's actually positively charged on that surface, which is kind of weird. But that's what would happen. Because all of the negative charge has been absorbed into the inside.
You can have the net charge of an object can be less than where charge is distributed on isolated places on the object.
That's right.
Okay.
Yeah, that's what these problems are about. It's about understanding that arrangements of charges can kind of alter how, this, if we removed this big 5Q object from here, right? If that wasn't there, all that negative 3Q would show up on the external of this object here. But by placing it on the inside, it has the effect of drawing negative charges inwards, right, in order to make this true. So there we go. And it also should make some kind of logical sense that if I have a spherical shell that's metal, it's reasonable to think that it could allow charges to basically move to the inner surface, basically, like this. So there we go. And that is the end of chapter... I don't know what chapter. I think it's 22, right? For Gauss's law. And next time we'll be talking about... I think electric potential is next. Is it potential or capacitors that's next? I don't know. Next chapter.
I think it's potential.
I think potential is next chapter.
Yeah, I think it's potential too. Because then the chapter after that's on capacitors. Because we need to know what electric potential is in order to talk about capacitors. But that's what we'll be doing over the next couple weeks. And I'm virtually certain that with everything that we've done up till now, you should be able to solve all of the lab manual problems. Pretty sure. Well, the last part of 379 does talk about potential, so we'll cover that next time. But for the most part, yeah, we've covered basically everything. So we'll stop right there, and if anyone does have any other questions, I will stick around.